I'm surprised that there's still so many people on Thursday afternoon. So I promise I'll do something to keep you a little bit awake. So the first thing is I'm going to start with a poll. So please show your hands if you use property testing. Okay. I expected more, but still fine for Thursday afternoon. Does anyone know when property testing got introduced? Any rough idea, rough year? 40s, 60s? It's a bit later. So Quick Check was first designed in 1999. So in case you don't remember, 1999 was a very exciting year. So those two competed for the top one in the charts. Then this paper was written. And while all this was raging on, this was me in elementary school completely unaware of any of this. So yeah, as I mentioned, it came out in 1999, so this paper is from ICFP 2000, the original Quick Check implementation. And I think you'll all agree that property testing has made our code better, right? I mean, Quick Check and the related tools, they uncover so many problems in our code. And also in Scala, I mean, Scala Check came out in 2007. I read a blog post the other day, it was kind of fascinating because the author wrote something like, property testing is an idea that came out of academia and it took less than 30 years to become basically pervasive. And that's fascinating, right? Because typically those ideas take longer to arrive in mainstream, but it took less than 30 years. And if you look on the Wikipedia page now for Quick Check, you will find that there's like a million different libraries for all the different languages. And even in Scala, we have multiple alternatives. So we have Scala props and Hedgehog. And you know, if you want to do property testing, you can do property testing. So it's one of our tools in the toolbox to write correct Scala programs. But there's, of course, more tools in our toolbox, right? So, you know, property testing is great, but we also have polymorphism, and in particular, type constructor polymorphism. So, if you want to know all about that origin story, ask Adrian, because he did it for Scala in his PhD thesis. This sort of programming construct that we have in Scala allows us to be so abstract that it's very hard to introduce bugs in the first place, because we express our programs in such a way that it just makes it very difficult to introduce bugs in the first place. We also have immutability, of course. I mean, I don't think I need to sell you to immutability. I mean, obviously that increases the correctness of our programs. But my talk wasn't titled How to Write Almost Correct Scala Programs. It was How to Write Correct Scala Programs. So now I have the second question for you, and I think you might have to think a little bit harder about this question. So in your personal experience, in your code, has property testing ever failed to find a bug? Has that ever happened to you? Show of hands. Okay, yeah, that's a few people. Anyone wants to yell like 2 or 3 words what domain that was, where it failed to find a bug? Complex business domain, yeah? Yeah. Yeah. Big state space, I guess, is one of the problems, yeah. So this is actually one of the things that I put on this slide, anything with a large parameter space. So if you have a function that takes 5 integers, good luck, right? Another problem is anything that's really stateful. So Quick Check and the related tools, they have some ways to test stateful programs. So there's also something about concurrency there. But honestly, I don't think many people use it. And I don't know if that's because it's too hard to use or because it's not powerful enough, but probably also related to the state space, because as soon as you have like stateful programs or even parallel programs, the state space is just becomes too complex. And then also anything with graphs. So if you've ever tried to implement a graph algorithm, there's so many weird corner cases that you can run into. Those could be performance corner cases, or it could be like cycles or whatever. And if you try to generate this stuff at random, it's just very unlikely that you will exhibit these problems. But there can also be problems that lurk in code that looks simple. So for example, this piece of code. Imagine those are integers. So this is a line of code that you might find in a binary search implementation, right? So in binary search, you have a low point, you have a high point, and you're now looking in the middle. Can anyone tell what's wrong in this piece of code? Yes, thank you. This is why I love giving this talk at Scala conferences. I gave the same talk at a Java conference, and no one knew what was wrong with that code. Audience bashing always works great. So this is a problem because you might overflow here. So you have something that looks correct. I mean, it looks very simple, but it's actually not right. Okay, next question for the audience. Will Scala check find this bug? Who thinks that Scala check will find this bug? Okay, a few people. Who thinks that Scala check will not find the bug? Okay, let's check. So we are I put this in a property, and then I'm running check, and it turns out, yes, it finds that. Because Scala check generators are designed in such a way that they try out the corner cases first. So it will put in max int as a first thing, basically, or something that's, well, it's not entirely true. Like the random generators are somehow skewed in Scala check to exactly uncover this. So in this simple case, Scala check had our back. But what about this piece of code? So this is a function that is copy-pasted from the Java, from the JDK. So this is a piece of code that is executed when you run a sorting operation. Now, JDK, in case you don't know, uses a particularly optimized version of sorting, which is called timsort. So timsort is a version of merge sort, which, like, you know, it's a very long implementation. It tries to be very fast. And it turns out that timsort was broken for the longest time in the JDK. And the problem was that there was an area out of bounds exception. Now in this function you don't see it because of course you call it with some parameters in some context, but it was part of a long implementation of timsort, and a paper came out that basically said Java util collection.sort is broken. And they could not, like, this is something that you, like, I would argue that the JDK is probably one of the best tested pieces of technology out there. I mean, there's like many years of engineering went into the JDK, and still this problem occurred, right? And it was like a really weird combination of corner cases when you had a very long array and there were like specific situations in the array, and then it was triggered. So it's basically, it was almost correct. Like this bug appeared very rarely, but almost correct is not correct. So what do we do? So I'm trying to sell you on a fix now. In fact, I'm going to sell you on two fixes. So there are some tools that allow you to actually write correct Scala programs, and with correct, I mean correct with respect to a specification. So if you don't have a specification, well, then I don't know what to tell you. I mean, this is always relative to a specification, and if you want to know how to write a specification, then ask our keynote speaker from this morning. He talked about this. So there's two tools out there. So the first tool is called Stainless. And if you want to learn about Stainless, talk to Viktor Kunčak. He's also a professor at EPFL. Stainless is a tool that allows you to annotate your Scala programs with basic annotations like require and ensuring and assert and so on. And it's kind of running the compiler plus some extra phases. So it's trying to figure out if it can prove that your annotations are actually correct. Now, I'm not going to talk about this one. Stainless is an interesting tool, and there's also some posters outside that explain how it works. But in this talk, I will talk about another tool, which is called Isabelle. Has anyone heard of Isabelle before? Yeah, of course, I know that you have probably heard of it. But okay, so a few people. So for the people who have not heard of Isabelle, here's the headlines. So it's a proof assistant, and a proof assistant means that I can write formal mathematics. So it's basically an editor where I can type in mathematical notation, and then I can type in proofs. So I can say prove this by induction, prove this by case distinction, whatever. So I can do the whole thing that I would do in a math textbook in order to do some proofs, but the system will check it for me. If I make a mistake, it will yell at me. So it's kind of like think of it as like a turbocharged type checker. So it will actually look at all of these individual steps and see if they make sense. I mentioned here various logics because there is not just one mathematical logic, and the one that we're interested in mostly is called higher order logic, HOL. Some of you may have heard predicate logic or first order logic from mathematics studies. It's like that, just a little bit better. There's other logics out there, for example, a type theory or set theory, but this is for the purpose of this talk, this is largely academic. So we only care about this higher order logic here. And I will explain to you why you should care in a moment. What also happens is that when you download and start Isabelle, it kind of looks like an IDE with a programming language in it. It looks a bit old-fashioned because we still use gedit, which is like VS Code but 15 years ago, but it works. So yeah, and the cool thing is that HOL, as implemented in Isabelle, is basically functional programming plus logic. So many of the things that you will see in this presentation will somehow, they will look strange, but you will somehow recognize the patterns going on there. So we have data types, we have recursive functions, and on top of that, we also have some proofs. All right, so that should be it for the intro. Let's go to the demo, because I did bring you a basic program and some proofs that I want to do together with you. Should show everything already. And it's about trees, because who doesn't like trees, right? Where's my cursor? The screen is too big. I can't fit my cursor. There we go. Okay. So, as you see, this is an IDE. And there's something like a module system, so you can import stuff. And we always import main because that's where the main logic is. And now we can do something like defining a data type. So in case there's anyone in this room who has ever used standard ML, this prime A is a type variable, right? So in Scala, we would write something like some tree A. So this is what this means. It's a bit arcane. So the syntax was devised in the 80s. So, and in the 80s, ML was the dominant syntax that you would use for something like that. Now a tree is a leaf, or we have a node. And the node, of course, has some elements. Now, the syntax is also a bit wild, so I need to walk you through it. I think this or is probably not a problem, so you have a leaf or, so this is also something that you would know from Haskell probably. And then you have a node, and the node has 3 parameters. So it's got the left tree, a value, and the right tree. There's a reason why you put these quotation marks there. It's not a string. Try not to think about this as a string. It's weird. just deal with it. If you want to, you can give these things also names. So you could say something like left is a tree, and then something like val is this, and right is also a tree. So, you know, you can give this names. And then now it sort of almost looks like a case class, right? If you give these things names. Another cool thing is that in Isabelle, you can always just ask for a value of something. So I can say, like, print me this tree. And now it can't do that because it doesn't know what the 3 is, because you need to be specific. Mathematicians don't just have a 3, it needs to be 3 of a certain type. So let's say this is a natural number. And now it will print that. So there's nothing exciting going on here. If you try to be more fancy, like you can say something like 3 plus 4, and then it will, need to put in more parentheses. And now you will see this is 7. So it's kind of like always live evaluated. So this IDE has everything, including syntax highlighting, but you can also like control click. So if you click here, if you don't know what it is, it jumps to the definition. So it's basically, it's got everything that you would expect from a modern. Did I actually click? No, I didn't click. Nope. So it jumps there. So you see this is defined there. So it's got everything that you would expect from a modern IDE, just it looks a bit old-fashioned. Now, let's try to define some things on these trees. So welcome to CS 101. We're now going to do basic data structures. The first thing that I want to show you is how to traverse the tree. So we can define like an in-order or pre-order traverse or something like that. In-order is the one that is relevant when you want to do like a search tree. So when you have these elements in order, then in-order will give you this ordered list. So let's define a function, and because, again, this is ML-inspired syntax, we're going to have fun with the functions. So this is called fun. I could give a type annotation here, but I can't be bothered, so let's just ignore that. So I can say in order traversal of a leaf is the empty list, because if I have a leaf, there's nothing in there. And you see already here, the system is already telling me something. It's telling me, oh, there's something undefined here. So this is just a warning. It's not really an error, but we know that we should be taking warnings seriously, so I'm going to fix it now. And I'm going to define the missing case for when I'm traversing a node. So I have to do a recursion on this. And now it gets, there's even more weird syntax. So there's an operator that we need to use to concatenate two lists. And that operator is obviously the @ symbol, because of course it is. Okay, I did something wrong. Yes. Okay, I need to delete the names again, because now there's a clash. It doesn't like the fact that this is a variable and this is a constant over there. So I tried to make it more readable, but in fact I messed up the system. So let's just get rid of those names here again. Oops. 1 second. So one of the things that Isabelle does very well is tracking of names and dependencies. So it's really, really strict about what sort of names you use, and like it does not, for example, allow you to do circular dependencies in definitions, because if you have a circular dependency, that means you might be able to prove a contradiction of something that's not really true. So it's really specific about the sort of things that it accepts. But now it accepts it, so we see no more warning here. And we can even try this out. So let me just copy paste this. And instead of just printing the full node, I'm just going to print the in order traversal of that. So in order. This, and you see there's a list now. So we get one item here. So that wasn't too exciting, I guess. Anyway, why am I showing you this at the Scala conference? Right? Because I talked about how to write correct Scala programs. So first of all, I have not shown you how to prove anything correct, and I also have not shown you yet how this is related to Scala at all. So I'm gonna show you one thing quickly now, and then we're gonna pick that up later again. What Isabelle allows you to do is it allows you to export these definitions into a programming language. So, because this one really doesn't have any compiler, like you cannot compile this and then run it. The only way you can run stuff if you use this value command to evaluate something in line, but ideally you want to run this on arbitrary user input, right? So you need to translate this into a programming language which then can be compiled. And it's got something for that, so it's called export code. And I can say export please this in order, and then I have a choice of languages, and of course here I would use Scala. So what this does is it looks at all of the definitions that are relevant for in-order traversal. And once again, I can click on this. And then you see this, you have an export file. And now you have a Scala program. And I guess this is not how you would write it down, but you can recognize it, right? You can recognize it as a tree. It's a trait with some case classes implementing it, and then you have a pattern match. So this is basically the connection. This is why you're sitting and listening to this talk at the Scala conference, because we have this facility here. We also have a bunch of other languages, which I will talk about in a moment, but let's try to do something interesting first. So let's get rid of that again. Typically, as a theoretical computer science, as a theoretical computer scientist, you can't be bothered with actually running programs. So like, let's just ignore that for now. Like, it's just to appease the programmers. We can do it if you want to. Like, if you really want to run programs, you can do it. But you know, you don't have to. It's perfectly fine just to prove things correct. Now, one interesting property that we could be proving about this in-order function is that all of the values that are in the tree are also in the traversal of the tree, right? So in-order is a function that takes in the tree and produces a list, and we want to make sure that the elements that are in there are the same. Now this is where high-order logic is cool, because you have sets, and now you might be wondering, well, we have sets in Scala, right? But the sets in Scala are not really mathematical sets, because in Isabelle, sets can contain anything, and they can also be infinitely large. So we can just reason like set theory, so we can do pretty much whatever we want with those sets. And now we can write our first lemma. So I hope you're excited for the first proof that you're seeing here. So what we're trying to prove is that the set that we get out of the in-order traversal is the same as the elements that are in the tree. So we write set of in-order t. So set is a function that turns a list into a set. And then for the tree, we also have a set function, which is called set tree. Right. So it says, okay, challenge accepted. Let's now try to prove this. So here you get also this immediate feedback. So this is always there, this kind of panel at the bottom, which tells you this is what you have to do now. So instead of a warning, this is now a goal that you have to show. So who here remembers mathematics class and has any idea of how we would prove this? What is your favorite? What is every computer scientist's favorite proof method? Induction, yes, structural induction, exactly. So fortunately, we can write exactly that in Isabelle. So we can say apply induction, and we need to tell it what to do the induction over. So what has happened now is we're kind of applied what's called a proof method. So we're taking an existing goal, we're applying a method to it, and now we have a hopefully better goal, or like an easier goal to prove. Like we have made progress in our proof. And as you would expect, you now get two sub-goals, because we have a case for leaf and we have a case for node. Unfortunately, this doesn't look very easy to analyze, because you have all of these, like, it's quite a long list here of things that you need to prove. So it's not really very structured. So, and it's also not how you would see it in a textbook. Like if you're opening a textbook, this is not like a math textbook, you would not be looking at a proof like this. They don't write apply or something. So what we can do instead is, instead of using apply, we can write proof. And then what the system does, if you know where to look, it generates a template for you. So it has now generated a template which looks more natural. So you now get these two cases that you need to prove individually. And another funny thing about the syntax is that if you want to check the proof, like if you want to check the overall structure of the proof, but you don't know how to prove the individual case, you just type sorry. So you kind of like apologize, like I don't know what to do here for now, but just accept it as truth. So here the system will accept those two subcases as truth and not bother you very much with it. Now, fortunately, filling in these cases is not actually hard. So the system has a lot of automation. So what I can just do here, I can just type by auto. Why can I type in by auto? Because the proof is simple enough for the machine to come up with itself. By the way, we have a lot of tools that will automate this. So there's a method that's called auto. There's a method that's called force. And if all of this fails, the font is a little too small, but there's a button here that says sledgehammer. So there's a tool that's called sledgehammer, which will basically just fork out to 5 or 6 different other tools that's trying to like work on the tool at the same time. So it's called a hammer because you're applying heavy machinery, and the name stuck. So all of the other systems now, they also have a hammer. So there's like all of the other proof systems, they have something like that. And this was using AI before AI was cool. Back when we called it machine learning. So it's trying to also learn from the way that the proofs are, like, depending on what kind of thing you're working on, it's trying to learn like what to do in order to make the proofs go through, and it's trying to take as much work off of you. The only thing that it can't do really well is induction. So for induction, we typically have to type first induction, and then many of the other things just work. Okay, so let's look at the time. I think we have still some time. So let's define another function, and let's make some more proofs. One of the biggest applications of binary trees is, of course, search trees, right? So search trees are a data structure where your elements in the tree are somehow arranged in a good order, and then you can use that in databases and whatever for efficient lookup. So first, let's define a function that tells us if a tree is actually a binary search tree. So we give this function an input, a tree, and then we want it to know if it's a tree or not. And for this one, I'm going to specify the type, because the type is actually interesting. So let's have some more fun here. So we still have to take the type parameter, and we now need to compare elements in this tree, right? So we need to compare that the left side is smaller than the right side. So we need a comparison operation, and Isabelle has type classes. So we can specify that this type parameter needs to be of a certain type class, which in this case would be lin order. So we need a linear order of elements. The cool thing is that you get the less than symbol also with order instead of lin order, because Isabelle allows you to be very specific about what kind of order you want. Do you want a partial order? Do you want a total order? Like, you can go into all of these details. For simplicity, let's just use lin order, because that's what most people would be using in a search tree. And did you notice I typed equals greater than, and it gave us this funky little Unicode arrow? There's a bunch more of those. So yeah, stay excited about this, because you're going to see more. So this is a function that returns wool, which mathematicians like to call a predicate. And why am I telling you this? Because mathematicians also like to write this. So a leaf is always a binary search tree, because in a leaf you have nothing, so it's always ordered. And this is exactly what you would see in a mathematics book. So this system is really designed to appeal to both functional programmers, because you have data types and functions, but also the mathematicians, because they will look at it like, it's not like a triple equals sign that I've never seen in my life before. That's this funny thing for Booleans. So it's the equivalence of Booleans. I recognize this. Right, so how would we define this now for this? Okay, now this gets a bit more involved, because now we have to first go recursively. We need to check if both the left and the right one are binary search trees, but we also need to compare the elements somehow. So let's get started first with this. Left. See, another Unicode symbol, so the mathematics conjunction. So in Scala you would write ampersand, but mathematicians don't like that, they don't recognize that. So we have to use this one. And the system will automatically recognize that, but if in case you don't know, you can also go to symbols here and you get the whole thing. So like, wait, which one? So Greek letters, for example, they're all at your fingertip if you ever want to do this sort of thing. Oh, and by the way, this system not only can compile to Scala, but also to LaTeX. So you also can get high-quality PDFs from it, in case you really, really don't want to execute your program. Okay, so we've got the recursion. Now we need to look at the elements. And we can now try to look if there's like a root element or something like that in left and right. But the easiest way to define this, instead of like doing further pattern matching, is just to say all elements left need to be smaller than the value, and all elements right need to be bigger than the value. So we're going to need to use a quantifier. So we have a little quantifier symbol here. We can say for all y that are an element of the left tree, y needs to be smaller than value. Syntax should be correct. Nope, because I call this val and not value. Okay. Right. So you see, this is basically, again, textbook notation. We're not ready yet, because we need to also do this for the right-hand side. For all y in set tree right, bigger than well.
Would it be enough to just check the next node and not all of them?
Yes, yes. So the question is, can we also just check the root in left and right? And we could do that. We would need to do a bit more pattern matching, right? So, but actually this is a very good question, because when you write this down, you don't really care about performance at all. You're just trying to describe this in the most abstract way. You would never implement this in Scala in this way. But at this point, you don't have to care, because it's never like, this is a high-level description of what's going on. So this is the easier description, and if you look at, like, if an algorithm person or a data structures person would look at it, they would say, yes, this is obviously correct. Now, a cool thing, I don't have time to go into this in detail, but the cool thing in Isabelle is when you actually do this export code and then you try to create executable code from it, you can give it optimizations. So you can say, well, if you recognize this pattern in the code, replace it with this one. And it makes you prove these optimizations. So you can say, well, if I have a smarter version of this, I just create a copy of this, and then make it faster, and then I have to prove that they're the same. So the system makes you work very hard in order to stay correct. You also have a question? Yeah, I guess you would have to need to carry like a stack of like the acceptable range. Yeah, so you would need to have additional parameters that tell you.
The left node can have under it on the right side more nodes that are greater, or by definition.
Yeah, see, this is what the system forces you to do. It forces you to think about this. So if we come up, I mean, we could do that now if we had time. We could come up with a smarter version and try to prove the equivalence. But this is actually not what, I mean, this is basically details in case you ever want to run stuff, which I don't. Yeah, we can try to define a bunch more functions. For example, we can try to prove that when you have a search tree, that when you take the in-order traversal, it's actually sorted. So you can, assuming that your tree is binary search tree, then the in-order function gives you like a sorted result. So let's try to write this down. So we use another lemma. And there's more textbook infrastructure that you have here. So you can write something like assume. So you assume that something is a binary search tree. And then it says shows. And then we say sorted in order T. So you say, if we have a search tree, and then we turn this into a list, then this list is going to be sorted. So this is the sort of thing that allows you, that Isabelle allows you to do. Now, let's say we mess up something here. Let's say we, instead of, let's just say we remove this part. Let's just say we mess up this BST function. What the system also does, it tries to find a counterexample. So this system also has a quick check built in, just as an assistance to you. So if you write down a theorem that the system thinks you won't be able to prove because the system thinks it's actually wrong, it will try to give you a counterexample and you're, yeah, maybe this function is actually bad. Of course, this is like a regular quick check implementation, but it has a bit more information at its disposal because it tries to be smart about the types because there's no type here. It's a generic type parameter. So it tries to even give you a small type. So it's not only not only randomly generating inputs, it's also randomly generating types that it's throwing at the thing. So it's actually quite smart and it's a good help. So I'm not sure if we can actually prove this with the stuff that we have. Let's try. So we have this assumption. Now quick check doesn't complain, so it thinks it could be right. So we can say using assumptions. And let's try to throw induction at it. And induction, of course, does something. It tries to simplify this. And then one thing that we need to prove, I think, is that this recursive case, this is still in order, like this is still sorted when we have a node. And when we do in order traversal of a node, we have an append function that we need. So let's see what it does. So I'm gonna try to smash auto at the problem, and it has proved something, but it has not proved everything. It now needs to prove. It now asks me to prove that a concatenation of lists is sorted. So fortunately, actually, let's try if Sledgehammer can do it. I haven't tested it. Let's just see. So this is the this is the point in time where like when you run spt clean compile, you get a coffee. So now let's see if it's doing something. I don't have the latest laptop, so it's trying to run like 6 or 7 different tools on my laptop. It's spinning up now. It's working very hard to find a proof. I think we're not lucky. Well, I have the proof here on my cheat sheet.
You're doing all of them in parallel?
Yes. Yeah.
So it could be fast if you just picked one.
Yeah, but yeah, it's telling me it has not found a proof sadness. Okay, so let's see. So the way that it wants it to prove is by force. No, I realized my mistake. I was missing a lemma. Because I think we have proved this lemma, but it doesn't know that it exists. We have not given this a name. We need this actually. Let's give it a name and do another magic incantation. And I think now, oops. Yep, no, it has done it. So we had everything in place, but if I don't give a name to a lemma, then it will not automatically find it. Maybe if I run Sledgehammer now, actually let's try. Maybe this was the problem why Sledgehammer didn't find it. Okay, in the meantime, I saw someone raising the hand, or no? Okay, anyway. Well, yeah?
So there are other proof assistants, right? Like
Yes.
Coke, this kind of stuff. And Idris, but that's not really a proof assistant, right?
I mean, sort of, yeah.
Sort of,
Yeah.
right, dependent type thingy. How would you, like, just a couple of words, like, why you choose as Isabelle instead of the other one?
So why did I choose Isabelle over the other ones? Well, I did my PhD with Isabelle, so the choice was made for me. now you see it found a proof, so yeah, great. CVC5 was also partly developed at EPFL, so yeah, it stays in the family. Okay, so I think Isabelle really has the best automation of all of them. So almost all of the other proof assistants are based on type theory, and it's just harder to automate. So here we have sort of like more tools at our disposal because we are using classical logic. So a lot of the proof techniques that you have in classical logic just do not easily work in constructive logic. There are disadvantages as well, but in my opinion, like this is very, 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 very fast. So yeah.
Can you say a couple of words on disadvantages?
On the disadvantages? Yeah, I mean, if you ask a mathematician, they would say, you know, with classical logics, you sometimes do proof by contradiction, which are proof with some axioms that they don't like. So you don't always get an executable program out of it. So when you do something in Rock or in Idris or something like that, you always get an executable program. Here, no. Here you have to be explicit about what's a program and what's a proof. Anyway, so I think this should be the extent of it. I could also show you again how the generated Scala program looks like, but I think you get the idea now. So you would export just the right bits that you need. So you would do like functions and lemmas and proofs and whatnot. And at some point, you export the stuff that you need, and then you can run it if you really want to. So given that we're running out of time, I'm wrapping up now. So I mentioned to you that you can export this to various different languages. Scala is one of the languages, but we also have Haskell and OCaml, which are first-class targets. And I'm a little bit ashamed to admit it, but me and a student implemented also this for Go. So if, like our company, you're using Go, you can do that. So we wrote a paper about it, and it was very hard because Go has no data types. It has no type classes, it's got nothing. So why would you do that in general, not just Go? Well, sometimes you need your code to be 100% correct, right? Sometimes it's just necessary. And why not? Well, this is a quote from John Hughes from another paper on QuickCheck, and he's trying to argue why property testing is a good middle ground. I'll give you a moment to read it. So what he's basically saying is that if you have one line of code, you need 10 lines of verification. And in many domains, that's just not a good business case. In some domains, it is. So I guess depending on what you're doing in your day job, come to me and ask how it works, or just think that this is an exercise that you don't need. Anyway, I hope you enjoyed this, and happy to take any questions. Do we have time for questions?
Like one.
Okay.
I have one question. Does Isabelle prove it mathematically, or will it run on my computer? Because the first example is completely the error in the sorting algorithm, low plus high divided by 2. It's perfectly mathematically correct. It just doesn't run on a computer.
Yes, so in Isabelle you need to be precise about what number type you're using. So most formalizations in Isabelle would use natural numbers and integers, which are mathematical natural numbers and integers. And if you generate this to Scala, it will use big int, for example. So it will not be running into this problem. You can tell it to use words. So you can tell it to use a 32-bit word or 64-bit word, in which case it will complain if you try to prove this, because it knows that the semantics for plus is different on words than on integers, right? So depending on what you're trying to do, you can use different number types. What you can also do is you can have two algorithms, and you make them abstract, for example, and then you plug in integers here and words there, and then you try to prove that they're equivalent under some boundary conditions. So let's say if you're putting in an array that's less than 100 elements, then they behave the same or something like that. So you can do that.
All right, thank you very much for the talk. And if you have more questions, then feel free to talk to Lars afterwards.
Thank you.